Hey folks, this is Professor Sills, and what I want to do is review Chapter 4 with you, and I think for this series of instructional lessons it's going to help if I use some visuals and also explain a few things. And if it works for you, then certainly feel free to replay this video really as often as you need, so that you can gain some sense of what I'm talking about and what the main ideas are. So let's get right into it. This is Chapter 4. We'll begin with question number 4. Explain why condensation occurs primarily when air is cooled. Well, from your reading, one of the things you should know is that when you cool air, for lack of a better explanation, it has less ability to hold the moisture. In other words, cold air cannot hold as much water vapor as warm air can. Classic evidence of that is, as we approach this season and New Jersey begins to warm up, you know that if you take a bottle of soda or something out of the refrigerator and do not open it, you will see moisture appear on the outside of the bottle. Where is it coming from? It's coming from the air, and it's coming from the fact that you're cooling the air and forcing the air immediately around that bottle to saturate. Saturation is a condition when there's when the air is holding as much water vapor, if you will, as it can, and therefore the water vapor is forced to condense. Jumping up to 6, condensation from precipitation. Well, condensation, as your book showed you, is very small droplets, and precipitation, rain, snow, sleet, is much larger, on an order of 1,000 times larger. In other words, condensation is small enough to actually levitate or remain suspended in the atmosphere. A classic example of that is fog. When you go out and it's foggy, the droplets that are there are not rain droplets. They're more like condensation droplets. They're very tiny, and they're capable of remaining suspended. Jumping number 8. In a volume of air, how does actual vapor pressure differ from saturation vapor pressure, and when are they the same? The actual vapor pressure is how much water vapor is really in the air. Saturation is how much it can hold. So if we look at relative humidity, it's the actual vapor pressure or density, if you will, as a ratio against the saturation vapor pressure or density. So what that's really saying to you is, when these two are the same, this would be like having 1 over 1 times 100%. Your relative humidity is 100%. Another way to put it is, the atmosphere is saturated when the actual vapor pressure equals the saturation vapor pressure. Now, how does that happen? One of two ways. You can either infuse more water vapor into the atmosphere, for example, a warm, moist air mass traveling up from the south, a maritime tropical air mass coming from where I am, up towards where you are, will bring more moisture into the atmosphere. The other way to do it is to lower the saturation vapor pressure. How do you do that? Saturation vapor pressure is temperature dependent. That's why fog is more common early in the morning. If you live in a valley, if you're up in, let's say, Wanacue or parts of Hawthorne, and you're in between two hills, you probably experience fog on a fairly regular basis, especially at this time of year when the water vapor is beginning to increase in the atmosphere. So number 9, I basically just explained it. Saturation vapor pressure primarily depends upon temperature. The warmer the air is, the more water vapor the air can hold. That is also, by the way, why in the summer, when it's 95 or 98 degrees out and it feels really humid, the reality is the relative humidity might only be 35%. Well, how does that happen? Relative humidity, remember, is a ratio of actual to saturation. Well, if the saturation is extremely large, really warm air can hold a lot of water vapor, so saturation would occur with a tremendous amount of water vapor. You're going to have a fairly small ratio here, because the actual water vapor in the air will always be much less, usually be much less, than the amount when the air is saturated. Down here in Florida, of course, we can get extreme humidity, and when you have saturation, when the air is about 80 or 85 degrees, that's just oppressive. And any of you who've ever been down in Florida or on a tropical island know exactly what I'm talking about. All right. Number 11, what does relative humidity represent? It's a ratio. It's a ratio of, again, how much is the actual vapor pressure or density to the saturation vapor pressure or density. When you hear the relative humidity, that's, again, in 11B, you want to know the air temperature, because an 80% humidity when it's 35 degrees Fahrenheit out is not anywhere near as humid as 80% humidity when it is 85 degrees Fahrenheit out, which again in New Jersey is very, very rare to see humidity that high at that high of a temperature. And again, letter C, how does relative humidity change? It will change if you change either of these two factors in the ratio. If you add more water vapor, it will go up, and if you lower the temperature, which lowers the saturation vapor pressure, it will go up. Now dew point, okay, backing up, on number 12, on a summer day, relative humidity will change as shown in figure 412. Well, I'm not looking at it, but easily enough, as the temperature goes up during the course of the day, the relative humidity should decrease even if the amount of water vapor remains the same. Why? Your denominator is changing. Hot, humid days usually feel hotter than hot, dry days. That's just the way we are. We sweat in order to cool off. And if we don't sweat, then we don't cool off. When it's humid out, your body is unable to have evaporation occur away from it, which is what cools the body. So in higher humidity conditions, higher dew point conditions, you're less comfortable, which leads me to number 16, dew point temperature. Dew point is the temperature at which saturation would occur. In other words, if I take a parcel of air and cool it off to the point where water vapor condenses into water droplets or ice crystals, that's the dew point temperature. So that's how dew point is defined. And the difference between dew point and air temperature related to relative humidity. All right, so the higher the air temperature is relative to the dew point, the lower the relative humidity would be. So if the dew point is 60 degrees, if we cool the air down to 60 degrees, we'll be at saturation. As we warm the air up above that 60 degree dew point, the air cannot go below 60. If we warm the air above that 60 degree dew point, then we're lowering the relative humidity. We are not changing the amount of water vapor in the air, and that's important to understand. So a dew point of 60 is a comfort factor. Many of us are comfortable up until a dew point of about 60. New Jersey, of course, is now headed into tropical season, and when you hit June, July, and August, your dew points are very often 70, 72 degrees, and that's what we call oppressive. Down here in Florida, we'll see the dew points at 78, sometimes even 80 degrees. Very, very oppressive. All right, number 17, cold polar air described as dry. Well, there are a couple of reasons for that. First of all, if we go to the source regions, continental polar air, continental Arctic air, cold polar air, first of all, originates over land. It's not going to have a lot of moisture. The second thing is it's cold, so it can't hold a lot of moisture. So when these continental polar air masses drift southeastward towards New Jersey in the winter, they're bringing in dry air because they have no moisture to begin with. In contrast, maritime tropical air masses, which originate over warm water sources. If you've ever been in the water in the Gulf or in the Caribbean, you know, or in the Southern Atlantic, that the waters get very warm, and warm water has a tendency to evaporate. So that means that there's tons of water vapor in the lower atmosphere in these regions, the Gulf, off the coast of Florida, and the Caribbean. And as this moisture heads northward, advex, if you will, courtesy of global wind circulation. If I go back to this diagram, here's where the global wind circulation comes in. We are in a belt, especially in New Jersey, called the westerlies. That means things generally travel from west to east. Clear that off. Things generally travel west to east. That's why, for example, Europe has a problem with the Icelandic volcano, which, by the way, has nothing to do with global warming. I heard the latest nonsense on the news this morning that the Icelandic volcano occurred because of global warming. Because the westerlies generally blow winds from west to east or southwest to northeast like this, they're going to carry anything dropped in the atmosphere eastward. Well, think of it this way. when you have smokestacks in Bayonne and in Staten Island that are polluting the atmosphere, where's that pollution going? Out into the Atlantic, east, pointing to my right. In Iceland, when you had the volcanic eruption recently, what are you getting? You're getting the smoke, the plume of ash particles to travel eastward, and that's why many of the airports in Europe are now shut down as of the time that I'm recording this. All right. Number 19, why is air from the Gulf of Mexico so much more humid than air from the Pacific at the same latitude? Well, you tell me. Think about it a second. I covered why air here has so much water vapor in it. What must we conclude about the water out here? And if your answer is the water is colder, that's the right answer. That's why, for example, if anybody's ever been out here and has tried going in the water, even at San Diego, which is roughly the same latitude as South Carolina, the water is much colder, and that's because of ocean currents. That's a story for another day, but the reality is the cool waters out here do not evaporate as much, therefore there's less water vapor in the atmosphere. Let's close this out with questions for thought. Number 2, how can frozen clothes dry outside in sub-freezing weather? The answer is sublimation. Sublimation is a process where ice will directly convert to water vapor without going through the liquid stage. So just remember that. Sublimation means going directly from solid to gas. Number 4, where in the U.S. would you go to experience the least variation in dew point? Well, let's look at the map again. If we look at the U.S., if you know your geography and your regions, this area of the U.S. is called the Desert Southwest. Arizona, New Mexico, and the interior of California. That area notably has very little moisture in the air, so logically, dew points are not going to vary much throughout the year. And lastly, number 11, evaporative coolers. I saw those for the first time myself a couple of years back. Evaporative coolers are an old method for cooling air. Why? Because evaporation absorbs heat. We've covered that point throughout the course. So as water evaporates, it will absorb heat. Now, if you place evaporative coolers in this area of the country where it is A, hot, and B, there's very little moisture in the atmosphere, then what that means is the water will evaporate fairly readily and absorb energy as it does. That will cool the room that the evaporative cooler is in. I actually traveled Route 66 a few years ago and found some of the old motels that were built back in the 20s and 30s before the days of air conditioning. Few of them still have active evaporative coolers. Well, with that, I'm going to close out this assignment, and I'm going to encourage you to keep working diligently on this as we only have a couple of more weeks. Thanks, and you have a great day or whenever you're watching this.